Approximate functions refers to things like interpolation and some related operations used in computing function values based on a few points along the function. For example, here's a list of values of a function at a few points and a plot of the points. Interpolation can be used to get approximate values of the function between those points. This input uses the interpolation function to get a value of the function at a point that falls between the points given in the original list. Interpolation returns an interpolating function expression, which is a special data structure that contains information that is useful for efficiently computing interpolated values of the function. The interpolating function expression works like a pure function and can be applied like a pure function to an argument to get an interpolated value. This shows a plot of the interpolation. This shows that plot together with the original points. Interpolation between the original points is done using polynomials that pass through those points. Interpolation by default uses cubic polynomials, which are polynomials of order 3. A polynomial of order 3 is determined by 4 points, and the interpolation is done by choosing points 4 at a time from the original list of points and constructing cubic polynomials that pass through each set of points. To illustrate how that works, this input uses the interpolating polynomial function to construct an explicit polynomial through the first 4 points in this list. And this shows a plot of the entire interpolation and the polynomial through the first 4 points. This constructs a polynomial through the next 4 points, and here is a plot showing the original points, the overall interpolation, and the interpolating polynomials shown as dashed lines that are used in that interpolation. In this example, the first polynomial is used for interpolating between the first 3 points, and the second polynomial is used for interpolating between the last 3 points. This approach of using different polynomials in different regions can also be set up using a function called piecewise. For example, this definition gives the same interpolation by specifying explicitly which polynomial to use for which values of the variable. Interpolating function expressions are much more compact and efficient than a construction like this, but piecewise can be useful in other applications. The order of the interpolating polynomials does not have to be 3. The order is controlled by the interpolation order option. For example, this input does interpolation with polynomials of order 1, which gives linear interpolation. And here's a plot of that interpolation. Linear interpolation corresponds to connecting the points with straight lines. The interpolations described so far always give plots with kinks where the interpolation switches from one polynomial to the next. A common way of getting rid of those kinks is spline interpolation, which is specified by giving spline as the value of the method option. And here's a plot of the resulting interpolation. Spline interpolation also uses polynomials, but with spline interpolation, the polynomials are constructed so that there aren't any kinks in the plot. For comparison, here's a plot of the earlier interpolation, which shows a kink where the interpolation switches from the first polynomial to the second polynomial. Mathematically, the kinks are discontinuities in the derivative of the interpolation. Spline interpolation requires that the first and second derivatives be continuous, which has the effect of giving an interpolation where the slope and the curvature at the end of one polynomial matches up with the slope and curvature at the start of the next polynomial, which eliminates the kinks. This effect also shows up in the derivatives. Interpolating function expressions can be differentiated just like other expressions. For example, this gives a derivative of the earlier polynomial interpolation, and a plot of that derivative shows the discontinuity in the slope at the location of the kink in the interpolation. Interpolation can be done in more than one dimension. For example, this constructs an array of points and a two-dimensional interpolating function expression based on those points. That interpolating function expression can be used in plots and in other calculations, just like the one-dimensional interpolations shown earlier. That same interpolation can also be constructed using a related function called list interpolation. The difference with list interpolation is that for list interpolation, the function values are given in a separate array. For example, this constructs an array with the same function values as in the previous example, and this uses list interpolation to get the same interpolation as before, with that array as the first argument in the list interpolation function and the ranges of the independent variables specified in the second argument. The list interpolation function is useful when the points to be interpolated are given in this form, with the function values in an array and the values of the independent variable forming a grid, which is specified in the second argument of the list interpolation function. Before closing, there are a few common situations where interpolation comes up but that do not start with points along the function. One example is the use of interpolating function expressions by the ndsolve function to represent the result for the numerical solution of a differential equation. For example, here is an ndsolve calculation, and here is a plot of the result. The solution to a differential equation is a function, and in the result from ndsolve, that function is represented as an interpolating function expression. ndsolve computes points and derivatives along the solution and uses both the points and the derivatives to construct the interpolating function expression. Another function that computes points along a function is function interpolation. For example, this shows function interpolation used to compute an interpolating function expressions to approximate a given function. The function interpolation function chooses points automatically to give a good approximation to the original function. The resulting interpolating function expression can be used just like any other interpolating function expression. Function interpolation is commonly used to get efficient numerical approximations for functions that are difficult to compute or that use a lot of time or memory to compute. Additional information about approximate functions can be found in the Wolfram documentation in the general tech note on numerical operations on data, mainly in the section on approximate functions and interpolation.